Hello everyone. This is one of the most exciting projects I've done. It's not quite there yet, but today we're taking a huge leap towards the end goal. I'm building a modular, 100% open source, 20 MHz bandwidth software-defined radio. I can't promise it'll beat the competition, but that's not the goal anyway. The goal is to try some things out, learn some things along the way, and hopefully end up with an SDR that'll do some of the things a $300 SDR does, but for a fraction of the cost. I'm hoping for $50 in parts, and then we'll see what that gets us. Last time, I already had the dual 20 MHz IQ sampling ADC working, but since I didn't have it connected to anything that could keep up with the data rate, I decided to see how much SDR magic we could get out of a 50-year-old CPU, the 6502. I managed to successfully run Goertzel's algorithm and demodulate a few tones, the very minimum of what we can call software-defined radio, but on the same chip that powered the Apple II and tons of the Commodore machines. Nowhere near the 20 MHz bandwidth we're going for, but fun to see how far we can get with a CPU from the 1970s. Today though, we're going to breach the barrier and actually get tens of megasamples processed. If you followed along, you might have noticed the PhaseLatch ADC board isn't just an Arduino-style shield, but also has a couple of unpopulated header rows. I designed that for hooking up a Cypress FX2LP board, and if you're familiar with that, you might be thinking, is he hooking up a logic analyzer to an ADC? Well, not quite, or not just. The FX2 is a relatively cheap microcontroller with a USB 2.0 interface and handy buffers for streaming lots of data. That makes it a pretty good 16-channel logic analyzer, but with 480 megabits of USB bandwidth and just the right amount of glue, it's also super well suited as the bridge we need to get the data from the ADC to SDR software on a slightly more powerful computer than a 6502. The FX2 is actually based on an 8051 core, which I'd love to talk more about, but that subject might have to wait for another day. I've hooked up the FX2 to the ADC in a way that lets us sample all 10 bits of the ADC data by using all 8 bits of one port and 2 bits on another, or to double the data rate by ignoring the least significant bits. That leaves us with a choice in software to choose if we want 10 bits of dynamic range with limited bandwidth, or go down to 8 bits of dynamic range for maximum bandwidth. Conveniently, the FX2 can also output its own interface clock, so we can use that to set the sample rate. We have to read the ADC twice per ADC clock because the outputs are multiplexed. So we divide down the FX2 clock with a flip-flop and use that to clock the ADC. This might be getting a bit technical already, but the main point is, since the FX2 conveniently has USB, buffers, and a parallel interface perfect for the ADC, we can skip one of the most expensive parts found on a 20 MHz SDR, the FPGA. Unfortunately though, the main IC seems to have gone out of production, and I see prices for remaining stock go up on sites like LCSC, even though you can still get dev boards for around $5. I've linked the dev board in the description. Let's see how long stocks last. Since everything happens to line up, we don't have to bit shuffle as much, and we save a bit of cash and a lot of complexity. But does it actually work? I've soldered it up, so let's plug it in and give our USB bridge some code. All the code is available on my GitHub, and it should be pretty easy to get running with open tools. I haven't written a SOAP-compatible driver or anything like that, but just what we need to get the data to our choice of SDR app. The code for the FX2 does the bare minimum of outputting the clock and buffering the data to the USB endpoint. Since the available clocks are 30 and 48 MHz and we divide by 2, we end up with a 15 MHz sample rate for now, since 24 MHz would be overclocking the ADC. The host side code takes over from there and simply dumps the data from USB with reasonable buffering, and from there we convert the incoming 8 or 16-bit data to 32-bit floats used by GQRX. Like the PhaseLatch Mini, this means we just pipe the data to a FIFO on the computer and let GQRX read that like a file. And we define the frequency and sample rate that matches the data. Maybe someone will help me make it into a real SOAPy SDR driver. Maybe you. Any help appreciated. Stop by the Hackerspace Clubhouse on Discord if you have ideas. Invite in a comment below. In general, I lose interest in the software about the time it's good enough to prove the board works, but I really appreciate when someone takes the time to make the software accessible. Just to recap, what I have on the table here is just a wire antenna going into an FM bandpass filter that we mix down to baseband using the PhaseLoom IQ mixer, into an anti-aliasing filter over to the PhaseLatch ADC, and then finally over to the computer using the FX2 board. There's no amplification, AGC, or front-end premixing yet, so for now we're stuck with the frequency range of the SI5351 on the PhaseLoom. But that should still give us decent FM radio reception. But let's take a look. I've got it tuned to a talk radio station to limit the risk of a copyright strike, and hopefully I can get better signal by unfolding the antenna a bit.
Dansegulvet bliver åbnet af selveste Mark Anthony, som er DJ, og han kalder Mr. and Mrs. Beckham op på dansegulvet for at have deres første dans. Og det er jo en kæmpe ting i England og USA. Det er, når man har den første dans som par, som ægtepar.
That does seem to help a bit, and by the look of it, we get about 20 dB of signal over the noise. With only the mixer output buffer as amplification and a random wire antenna, I think that's pretty decent for a not too strong FM station. But, I do believe one of my ADC filters are acting up, or I have a bug in the code on the PhaseLoom, since mirror suppression seems almost non-existent. I'm sure we can clear that up. For a $5 USB board and a $3 ADC, this has to be the cheapest way to get 40 million 8-bit samples per second into a computer. Before we move on, I'd like to try something a little bit crazy. It's a 20 MHz ADC, but the FX2 board only outputs either 48 or 30 MHz. And I'm super excited we're actually looking at 15 MHz of instantaneous digital bandwidth because we're using the 30 MHz clock divided down. But what happens if we use the 48 MHz clock? Can we still get data out of the ADC clocked at 24 MHz? Well, this is technically 24 MHz of instantaneous bandwidth, but it does look like a bunch of different problems compounding into something not quite usable. The signal wasn't amazing to begin with, and we're probably introducing tons of jitter and phase noise and who knows what. So overclocking the ADC by 20% isn't doing us any good right now. Maybe we can still use it to our advantage later. So clocking the ADC from the divided down 15 MHz FX2LP interface clock works perfectly, but not so much at 24 MHz. Does that mean we're stuck with only one sample rate option? No. Actually, I mainly intend to drive the ADC clock from the SI5351 on the PhaseLoom, since we're only using 2 out of the 3 available outputs, and the other 2 need to be running from the same PLL anyway. To make that happen though, I need to change some of the solder jumpers on the PhaseLatch back to the default setting of using the clock input rather than the FX2. I've wired up 2 Schmidt trigger NAND gates as inverters, so I have some mobility of the phase delay of the sampling clock by jumping one or both inverters, in case we need it. If you're going to try this at home, make sure you take a good look at the schematic so you don't short anything. Since we're no longer using the FX2 for generating the clock, we need to set that as an input instead of an output. Now might be a good time to mention that although the FX2 does have an EEPROM to store some code, I'm currently only uploading to RAM, so every time I turn it on, I have to reflash the device. Fortunately, that's basically instant. Now let's see what the PhaseLatch and FX2 think about the 20 MHz signal. We immediately see the expected 10 MHz bandwidth, and luckily the mirror suppression issue seems to have vanished. Yay! There does seem to be a different issue though. It looks like INQ randomly swaps around, and there's a higher noise floor when INQ are swapped. Since I'm not packaging the ADC data in any way, but simply reading the raw data and blasting it via USB, the risk is that a single missed byte will misalign all the data. And also, if the flip-flop I'm using to divide down the clock misses a beat or picks up noise, we'll see the same issue. More testing needed, but for now, I'm pretty happy we're seemingly getting a clean 10 MHz from the external clock. Since the RAM on the PhaseLatch didn't work the first time because it had the wrong footprint and there's already a ton of easy improvements, I am happy to announce that through the power of editing and the sponsor of this video, I already have a new and improved board to try out. As always, JLC PCB is my favorite way to boost my efficiency by getting a new revision in no time. They're super reliable, and I'm always impressed how they can manufacture, assemble, and get the PCBs out the door in less than a week. I've used a 4-layer design for this board, but I actually wish I just went with a 6-layer one from the beginning. Since it doesn't just make it easier to place components, it's also so much better for any RF or high frequency work because you can have an unbroken reference ground plane under both top and bottom layers, and still have power planes or signal layers sandwiched in between. So much more predictable and easier to route as well. 6-layer PCBs are usually expensive, but at JLC I'm having a hard time justifying the 4-layer approach for this board, and their free VIA and pad support, I could have made the design much denser and placed more neatly. You can even grab a $30 coupon for your first 6-layer PCB order and get one PCB for just $2. If you're a new customer, you even get $123 of new customer coupons. Thanks to JLC for making it easy to get professional PCBs that give more routing freedom, faster development iteration, and successful projects faster. Super cool. The neat thing about the new revision is that I added 10 MHz low-pass filters to the ADC inputs, so I don't need the external phase blades like before, unless I need an even tighter analog filter. I also simplified the power interface a bit, so you don't need to manually jump the ADC digital supply voltage, and for this test, since we're using the FX2LP, all we have to do is add the headers and a jumper to power the PhaseLatch from the FX2. I'm not sure it's the cleanest of power supplies for an ADC, but I'm convinced it'll supply the current we need. Of course, it's meant to be a modular system where each module can stack on top of each other, but since the FX2 can't be used at the same time as the ADC is connected to a 6502 bus, I won't bother soldering in any more headers than what we need. Just 4 10-pin female headers and a jumper to connect power from the FX2 3.3 volt rail. Oh, and I forgot the clock select header. If nothing is clocking the ADC output mux, we're not going to get very interesting data. Let's see if the new board doesn't give us some sort of improvement. Before, we did see a sort of weird raised noise floor, but now we're back to the almost bell-shaped FFT. Why is it bell-shaped? Well, I'll get back to that in a bit. For now, I'm just super happy we're actually looking at a whole 10 MHz of digital spectrum all at once, and nothing is super unexpected on the negative side of things. You'll notice the spur at 96 MHz, which the seasoned radio amateur will immediately recognize as a multiple of 8 MHz and all the frequencies we have divided it down to on the 65 Uino currently driving the phase loom. Unfortunately, it doesn't take a ton of energy near our antenna input to show up like that. So that one might not be so easy to get rid of, since those 6502 clocks do get around a lot. But I'm sure we can find a few things to try later. And that's not all. The FX2 is running at 48 MHz from a 12 MHz crystal, which, you guessed it, both add to the spur at 96 MHz. For now though, let's charge ahead and see if we get the same success at 20 MHz bandwidth. To increase the sample rate, we'll need to change the 20 MHz clock from clock 2 of the phase loom to a solid 40 MHz and hope it'll stay somewhat coherent until it reaches the ADC clock input. If my math is correct, we can just change our divisor here from 8 to 4 and we should divide the 400 MHz PLL by 10 instead of 20 for a 40 MHz output. If you're new around here and wonder why I'm using an EEPROM programmer board to update the code, that is a very long story, but if you've made it this far, you might want to look around the channel. The short story is that for now I am happy with the roots of this project being visible, and the 6502 is more than capable of being the brains behind controlling this SDR. Now let's see what we get. That doesn't sound right, but of course we haven't manually changed the sample rate yet.
Men selvom ministeriet vil forsøge at hjælpe, skal de rejsende selv betale for deres flybillet, siger Lars Løkke Rasmussen.
Dansk lovgivning er sådan indrettet, at vi kan ikke afholde folks transportudgifter.
Oh, I guess my math is off by a bit. There, that should do it.
At sælge bøgerne. Søren Kierkegaards bøger, som vi lige hørte, han hed. Og det blev til en historie, både i aviserne og i radioen, for hvorfor gjorde hun det, når hun nu helst så, at bøgerne blev i Danmark? Måske tragiske eventyr lige om lidt.
And now it looks like we actually have 20 megahertz worth of digital bandwidth. That's almost what we're going for, and the reason I say almost is that we still have that almost bell-shaped FFT, and the waterfall quickly turns blue as we move away from the center frequency. The problem is, we've reached the point where the analog bandwidth can't keep up with the digital one. The PhaseLatch ADC can sample 20 MHz of bandwidth, but the phase loom doing the mixing and buffering just doesn't deliver a wide enough signal. If we unplug the two, we should see a flatter curve. Of course, the incoming data won't be IQ, but we should still see whatever noise comes from using the FX2. Just unplugging, we see a flatter curve. Let's call it flat-ish for now, but we also see some pretty nasty spurs around 5 MHz. Since that happens to be our sampling frequency divided by 4, I suspect it might be that coupling into the unterminated ADC input. It could also be external noise from the power supply or whatever I have around my office, but we have no way of knowing without a more reasonable test than listening to FM radio. So we'll need to make a little test setup to verify what's going on. After we have that in place, we can start trying to improve the analog bandwidth. Instead of a random piece of wire going into the phase loom, I've hooked it up to my scope and signal generator. The built-in signal generator of my scope doesn't generate sine waves all the way up in the FM band, but I'm willing to bet the phase loom mixer will happily show us the third harmonic of 31 MHz at 93 MHz. This won't be a super scientific test, but it'll give us an idea of the analog bandwidth we actually have. I'm feeding it a pretty strong signal, and it shows up in our FFT at -20 dB when it's near the center frequency. Usually when we talk about bandwidth, we mean the part of the signal that's less than 3 dB attenuated. On a scale like this, 3 dB might not seem like a lot, but in real numbers, it's half the power. Just to confirm we have the right signal, we can switch to single sideband mode and give it a listen while we change the frequency. Not that it should sound like music to anyone's ears, so let's turn that off and look at the graph. Just a few kilohertz away and we suddenly see a 10 dB drop. As we move even further away, the drop might not seem so dramatic, as we can still measure the signal a decent amount over the noise level. But when we look at the numbers, we see we're already down to the -60 dB mark. It just happens to be our luck. The noise floor is attenuated as well, but that doesn't make it very practical. Considering we started at -20 dB, that's a 40 dB drop. That's a factor of 10,000. 10,000 times less signal is hitting the ADC. And that's just about 2 MHz off center. Nowhere near the 20 MHz bandwidth we're aiming for. If we go back near center, we can measure our real -3 dB point. Our center point is 93.35 MHz, and we get about a 6 dB drop when crossing 93 MHz, so it looks like -3 dB is 93.025. In other words, 325 kHz off center means we have an analog bandwidth of 650 kHz. 650 kHz was fine when we were using a sound card or the 6502 that couldn't keep up digitally anyway, but now we need to up that quite a bit. So, what's causing the bell shape hitting the ADC? Well, over on the phase loom, we have two things in charge of the analog bandwidth. First of all, we have the mixer's inherent bandwidth, but we'll save that for later, because the prime suspect right now is the buffer op-amp. Actually, I picked the ADA 4891 op-amp because it has great bandwidth. If we look at the datasheet, we'll see it's supposed to have a -3 dB bandwidth of a whopping 220 MHz. So why does it roll off so sharply at almost 100 times less than that? It comes down to gain. The bandwidth drops dramatically as we increase the gain, but since we haven't needed the bandwidth until now, I've traded it for some free signal gain. Also, sacrificing flatness in the process. If we look at figure 7 of the datasheet, we see that a gain of 10 has the gain starting to drop off at 3 MHz, which doesn't sound so bad until I tell you that the 22K feedback resistor makes the gain 55. We don't need to do much extrapolation to see that won't give us very wide bandwidth. If I'm reading the figure right, we should be able to get away with a gain of +5 and still keep the bandwidth reasonably wide. We're going to need a decent low noise amplifier front end at some point, but let's see what we get. To drop the gain down, we can just divide our feedback resistor by 10, and that should give us a gain of 5.5 with a 2200 ohm feedback resistor. Since we're changing the phase loom, I'll also remove the 10 microfarad output capacitors as they won't do us any good, and worst case will create ripple in the filters on the PhaseLatch. It's not exactly the first time I've experimented with this board, so it's starting to look like a bit of a mess. It'll have to do until I get a new board. Let's see what we get with the lower gain. We should see a much flatter curve, but maybe still with some drop off. Oh wow, that is not what I expected. It looks like a ridiculously strong signal at around 2 MHz. It doesn't seem to change when I change the input frequency, so something is horribly off. I think I saw something about this in the datasheet. It says that a highly capacitive load reacts with the output impedance of the amplifiers, causing a loss of phase margin and subsequent peaking or even oscillation. Are we doing that? I thought we were only driving a pretty high impedance ADC, right? Well, not exactly. The low-pass filter starts out with a 330 picofarad cap to ground, which, as far as the op-amp is concerned, is absolutely a capacitive load. If I put my finger on the feedback network, we can even see the frequency change slightly. But how do we fix it? Lucky for us, the datasheet seems to have us covered. First, it suggests reducing the resistive load, but considering the ADC input is high impedance already, that's not exactly an option. Second, it suggests increasing the loop gain, but that won't work as that's where we came from. Third, it suggests adding a feedback capacitor, and I think I'll add that for the ultra-high frequencies, but I have a feeling the last suggestion of adding a series snub resistor will still be needed, so let's go with that. 100 ohms and 1.5 picofarads should improve things, so let's see. I guess a gain of 5.5 is still on the high end, because those bumps about 3 MHz away from center look suspiciously like the peaking the datasheet talks about. But the good news is we're now up to a -3 dB bandwidth of almost 6 MHz. It's not quite 20 MHz, but the cool thing is the math seems to hold up, and by decreasing the gain 10 times, we've increased the bandwidth 10 times. And even better, there's less ripple in the passband. Before we call it a day, let's see if we can't make it so the op-amp doesn't limit our bandwidth at all. If our rule of thumb holds true, the feedback resistor for a 20 MHz bandwidth should be about 667 ohms for a gain of 1 2/3. Let's give that a try. That combination does seem to flatten out the curve some more. Now the question is, if the last hump on the FFT is a result of the low pass on the PhaseLatch, or the inherent bandwidth of the phase loom, or the fact that we have a pair of jumper wires instead of traces, or there's inadequate component matching somewhere. I think we're at the point where we need to eliminate some variables by at least updating the phase loom. Smaller sampling caps should theoretically improve the bandwidth as well. But I think I'll need a new board if I'm going to experiment with replacing them. I am so excited that even though we're not looking at 20 MHz super flat -3 dB bandwidth, we are actually looking at 20 MHz of bandwidth somewhat within the same 10 dB. And if I amplified the incoming signal a bit, we actually could see the whole FM band at once. That's the sort of thing we're going for here. A $5 USB bridge and a $3 ADC plus some PCB and passives suddenly turned the SDR we started at 44 kHz into a 20 MHz-ish SDR. We're nowhere near professional grade SDR quality here, but for the price, I'm impressed this is possible. After recording this, I actually did improve the mirror rejection and flatness with a bit of bias correction like we did for the PhaseLatch Mini a while ago. But we can take a look at that again when we have a new and improved phase loom. If you want to play along at home, the code and design files are all on GitHub, and you can also just buy the boards I have left over on my web shop. I ship to about 50 countries. If you've made it this far, thanks for sticking around for a video that's a bit longer and more technical than usual. I could have skipped a bunch of the experimentation and trials, but building an SDR like this really is about the journey and not so much the destination, even if we do end up with an awesome SDR in a few episodes. Either way, thanks for watching.